Okay, everybody, this is the snow day lecture on Monday the 2nd of December, and we're in chapter 10.1 in the text if you're following along. So we're back to rings after studying groups for a bit, and so the basic situation is that before we started talking about rings, they were a rather wide abstraction of some of the properties of a ring, of the ring of integers. So we started looking at the integers, we zoomed way out to rings in general, then we zoomed back in to look at rings of polynomials over a field. And so the ring of integers and the ring of polynomials over a field have some rather special properties that general rings do not have. So in particular, rings and polynomials over a field are integral domains. But even more than that, they have special properties which allow us to have a division algorithm in them. So really the key property that we used over and over again when we were talking about integers and polynomials over a field is the division algorithm. A lot of what we did followed from that. So what we're going to do is, rather than starting from the integers or polynomials and abstracting all the way out to rings, we're going to zoom back in slightly and look at a generalization of the integers and rings of polynomials over a field that isn't quite as wide as all rings, but so it's going to be a slightly wider class of rings, specialized rings that have a division algorithm. So that's what we're talking about, and those are called Euclidean domains, as we'll see. Okay, so an integral domain, just to remind you, if it's been a while, is a commutative ring with identity and no zero divisors. Okay, so remember, zero divisors, that means that if a, b equals 0, that implies that a is equal to 0, or b is equal to 0. Right? Okay. So, and for this lecture, so R is an integral domain for this lecture. Okay, so R is always an integral domain today. Great. So I'll be fighting against board space here, so just bear with me. Okay, so of course, examples of integral domains would be Z and the ring, any ring of polynomials over any field. Right, so field could be the real numbers, complex numbers, Z mod P, rational numbers, anything like that. Another class of examples which is going to be interesting for us going forward is the following. So you can take the integers and in some sense attach a square root of another integer. So here d is going to be a fixed integer. So d in z is fixed. And this is going to be a set of r plus s times square root of d, where r and s are themselves integers. Okay, so things like that. And yeah, so what you can see is that, this is always contained in the complex numbers. This is contained in the complex numbers. D could be negative here. If it's negative, it's contained in the complex numbers. If it's positive, it's contained in the reals. So the difference of any two things like this is another thing like that, and the product of any two things like that is another thing like that, just by foiling. So this is a subring of the complex numbers, and the complex numbers are an integral domain, so this thing is going to be an integral domain as well. And a particular example is so if you have set d equal to -1, then what we have is the square root of -1 is I, so we have z with I attached, and that gets a special name. So this is the ring of Gaussian integers. This is the Gaussian integers. Okay, so we'll be looking more at that as we go along. This is a very important example of an integral domain. And it will be an example of a Euclidean domain, as we'll see. Okay, so now we're just going to repeat some terminology that we used in the context of the integers and polynomials over a field. So some terminology and notation. Okay, so first thing is we'll say that A, so here A, B, C, etc. are elements of our integral domain. Okay, so we say A divides B if B is A times some C, right, for some C. And yeah, so this is read A divides B. Okay, so we've seen that before in other contexts, in other specific contexts, but this terminology works just fine, even in a general ring, not necessarily an integral domain. Okay, and we also have the notion of a unit, so U is a unit. So remember, a unit is just an invertible element of your ring, so that means there's an inverse. U is a unit if UV equals 1 for some V in the ring. And then we would say that V is U inverse. Okay. All right. And one thing you can note about a unit is that a unit divides anything in the ring. So if U is a unit and R is in R, then U divides R. And we can see that quite simply, just directly, because R is R times the identity, and if we have a unit, we can write the identity as the unit times its inverse, right? So R is equal, 1 is equal to U inverse, and we can just use the commutativity and rearrange this. Right, so we see U times something is R, and so that says that U divides R. Okay. All right. Yeah, and so, well, as we've seen before, the only thing with inverses in Z, and so plus minus 1 in Z are the only units. Also, in the ring of polynomials, so if you have a polynomial over a field, or even generally over an integral domain, then, well, yeah, never mind. Just think of a polynomial over a field. So if this is a polynomial over a field, oh yeah, what I want to say is the only units are the constant polynomials. So f of x has to be a constant polynomial to be a unit. Are all units. Okay, so that's the only thing that's a unit. We've seen that before. But we can look at some new examples. So, for example, 1 plus the square root of 2 in Z adjoin square root of 2 is a unit. Okay, so this is a unit. And why is that? Well, we can just find something that multiplies this and makes 1. Right, so this is just a plus b and a minus b. So this is a squared minus b squared. So in other words, it's 2 minus 1. This is 2 minus 1 when you FOIL, and that's 1. Right? So each of these things is a unit in this ring here. As another example, we can find all of the units in the Gaussian integers. So all units, find all units. So let's find all units in Z adjoined I. Right, so this is all of the r plus s times I where r and s are integers. Okay, and well, how do we do that? Well, so a unit in here would be something in here, u, such that there's a v where uv equals 1. And the typical way to study this is to, right, so this involves complex numbers, right? It involves this I here, this equation, is to produce an equation using just integers from this equation. And one very convenient way to do this, very ubiquitous and convenient way to do this, is to use the norm in the complex numbers, or the norm squared. So let me just remind you, we've talked about this before. I think in the context of maybe in the group section somewhere we talked about this, but anyway, if our u is x plus I, y, and this works in general for a complex number, so you can think of these x and y as real, not necessarily integers, then the norm squared, that's just x squared plus y squared. And so geometrically, you know, if you think of this as just a point in the plane, this is just the square distance of this point from the origin. And the nice properties that this has, so it has some nice properties, and that's basically that it works well with multiplication. So you have any two u and v, which are complex numbers, uv norm square is norm square u times norm square v. So this function is multiplicative, distributes well over multiplication, and also works for division too. So complex numbers are a field, so we can divide, and the square of a quotient like this is the quotient of the squared norms. Okay, so we can make use of that over here. So applying the norm here, right, 1 is a complex number, 1 plus 0i, so its norm is 1. So norm squared is 1, so we get 1 is equal to norm squared u times norm squared v. Right? But if you think about this, right, we're in the Gaussian integers, so the norm square here is the sum of squares of integers. So this is an integer, and this is an integer, and they're both non-negative. So the only non-negative integers which multiply together to be 1 is 1 and 1, right? Nothing else works, right? Because these have to be non-negative. So this implies that norm square of u is 1. And, well, if I think about that, that says that x squared plus y squared is 1. Right? So x squared plus y squared is 1. And again, these are both integers, right? So the only possibility is that one of these squares has to be 1 and the other has to be 0, right? So it's either that, that x is plus or minus 1 and y is 0, or y is plus or minus 1 and x is 0. So that immediately implies, because x and y are in integers, that u is either plus or minus 1, right, if x is plus or minus 1 and y is 0, or plus or minus I if x is 0 and y squared is 1. So this is either plus or minus 1 or plus or minus I. Okay, and so that's the only possibilities, right? So if u is a unit, then u has to be one of those four things, and each of those actually are units. So 1 is, of course, a unit. Negative 1 is a unit because negative 1 times 1, negative 1 is 1. And I and negative I, they're mutually units with each other. I times negative I is 1. So that equation says both I and negative I are units. So those are all the units in the Gaussian integers. Okay. All right. So now we know all of the units in the integers, the regular integers, the any polynomials over a field, and the Gaussian integers. We know all the units now. Okay. All right, so some more terminology. We would say that, so A and B are associate. So remember, we talked about this notion for polynomials. So basically, the thing is that if you take any old a in your ring, in your integral domain, any old a whatsoever, and you take a unit. Well, that unit divides a, right? So a is equal to u times something, right? So let's say that's b. I'll call that something b. So this u, since u divides everything, this is a trivial divisor, right? But then if we have this divisor, we have this other thing that pairs with it to divide a, right? So if u is a trivial divisor, b is kind of a trivial divisor too, right? So this thing is what's called an associate. Right? So you have the units which divide everything, and then the associates are the things that sort of pair up together with the units. So they're associate if exactly this equation holds. So if a is equal to b times u for some unit u. Okay, so they're sort of the flip side of units. They're trivial divisors of a particular element of your ring. Okay. Right, so here's an example. So in z adjoining the square root of 2, square root of 2 and 2 minus the square root of 2 are associates. And why is that? Well, that's just because 2 minus the square root of 2, if I factor square root of 2 out of this, I find this is square root of 2 times negative 1 plus square root of 2. Right? Factor square root of 2 out of this, I get minus 1. And square root of 2 out of 2, I get a square root of 2 left. And we saw this as a unit earlier, right? 1 plus root 2 and negative 1 plus root 2 were units because they multiply together to be 1. So we have a unit times square root of 2 is equal to this, right? So unit times something equal to something, that implies these are associates. Okay, so that's a non-trivial example there. All right. I was just thinking of something. Oh, right. I wanted to say that being associated is an equivalence relation. So anything is associate to itself. A is equal to a times 1. Right, so a, little box down here. A is equal to a times 1. If a equals bu, then that implies that b is equal to a u inverse. Right, and u inverse is a unit. I'm just multiplying by a u inverse here. So a is associated to b, then b is associated to a. And you can also check, so if a is equal to bu and b is equal to cu prime, then just plugging this thing into here, we get that a is equal to c times u prime, right? And product of units is a unit, so we have a is equal to c times a unit. So a and c are associates. So if a and b associate, if a and b associate, b and c associate, then a and c are associate. So that's an equivalence relation. So you can think about the if you have some particular unit element of your ring, all of the you can think about the ring as broken up into equivalence classes of associates. Okay, and then we also have the notion of a prime, what in the integers is called a prime. So when we were talking about polynomials, we called it irreducible, and the definition makes perfect sense here. It really just says that an irreducible is something which only has trivial divisors, and as we discussed, the trivial divisors are the units and the things that pair up with the units, which is just the associates. So if you have some non-zero element of your integral domain, then is irreducible. Is irreducible if p's only divisors are units and P's associates. Okay. So basically what we have here is that if you write P is equal to R times S, right, well, one of these has to be, so basically what happens is every time you have a factorization like this, one of these is going to have to be a unit. So for example, if both of these could be a unit potentially, that's fine. If one of them is a unit, then we're done. And if two of them are associates, so let's say one of these is an associate. So if at least one of these is an associate of P, so let's say S is equal to V times P, right? So where V is a unit, then we would have P is equal to R times S, but that's R times VP, right? And then because we have cancellation in the integral domain, we can cancel the P's and we get 1 is equal to R times V. And so that says that R is a unit, right? So at least one of these is always a unit here. And that's a little proposition in the book. So it's an equivalent way to say that something is irreducible, is that whenever you have a factorization of it, at least one of the factors is always a unit. Okay? Okay, so that's the notion of irreducible. Okay, and as I said, this recapitulates our definition when we were looking at polynomial rings over a field, and also generalizes the definition of prime in the integers. So here's an example. So I claim that 1 plus I in the Gaussian integers is irreducible. Okay, and how do I do this? Well, don't want to block here. Let's see. So if P is equal to R times S, I say, well, let's see. So P is 1 plus I. What I'm going to do is again use the norm function, norm squared. So norm squared of P, well, that's the norm squared of 1 plus I, right? So you have 1 plus 1 times I. So that's 1 squared plus 1 squared, right? So that's 2. And this is equal to R squared, norm S squared, right? And so what we have is two non-negative integers multiplying together to be 2, but 2 is prime. And since these are non-negative, that means that one of these is 2 and one of them is 1. Right? So without loss of generality, because these R and S are just arbitrary labels, we can say that, say, norm squared of R is equal to 1. Right? But we saw in our previous example that if you have a Gaussian integer squared, norm squared equal 1, that implies that R is plus or minus 1 or plus or minus I, right? Which is a unit. These are the units, right? So that implies R is a unit. Okay, so P is equal to a unit times something, and by definition, that other something has to be an associate, right? So this arbitrary factorization is in fact a factorization into a unit and an associate. So that means that P is irreducible by definition. Okay. So now we come to the main definition of this section of the text, which is that an integral domain, so a Euclidean domain is an integral domain and integral domain with a function delta So this function is defined on everything on the ring that's not the zero element. Okay, so I'm just forgetting out the ideal generated by zero there. And that function takes values in the non-negative integers, so 0, 1, 2, etc. Okay, so you have this function with the properties, with the following properties. Okay, so one is that delta of A is less than or equal to delta of AB for all A and B in the domain of that function delta. Okay, so really what this says, I'm going to call this C. This thing C here, right? This B is just totally arbitrary. So C here is totally arbitrary. It's a totally arbitrary thing which A divides, right? Anything that A divides is of this form, some A times something, right? So really this just says that if A divides C, right? So if A divides C, then delta of A is less than or equal to delta of C. Okay, so this delta is has like a monotonicity property with respect to division. So if A divides C, then delta of A is, so you think about this as A is less than C with respect to division in some sense. And that immediately implies that delta of A is less than or equal to delta of C. Okay, so that's one property. And then the second one, the real key thing is the division algorithm. So this allows you to see this function delta allows you to is a way of measuring the size of things in your ring, which plays nice with division with respect to divisibility, and it allows you to measure the size of a remainder under division. So that's what we come to now. So we assume that this function delta has the following property for any A and B not 0 in R. Right, so I'm going to consider dividing A by B. There exists Q and R, right, elements of our ring, such that A equals B times Q plus R. Right, so this is the quotient when we divide A by B, and this is the remainder. Right, and want to emphasize there's no I'm not telling you, there's no general algorithm that tells you how to do this division. It's just that the function delta, to satisfy this definition, there has to be for every A and B such a way of writing A like this in terms of B, and the function delta comes in the following way. So such that we have this expression for A in terms of B, and either R equals 0, right? So it was just the case that B divided A straight up, or the size of R as measured by delta is strictly less than the thing we're dividing by, right? So delta of R is less than delta of B. Okay, and that's just like it was in the division algorithm for the integers, right? When you divide by 5, you want your remainder to be less than 5. So you divide by B, you want your remainder to be less than B in the sense of this delta, whatever it is. Okay, so we have to have those two properties on this. There has to be a function with these two properties somehow in order for our integral domain to be a Euclidean domain. Okay, so if we take our ring to be the integers and delta of x to be the absolute value of x, then this defines a Euclidean domain. Okay, so why is that? Well, one, delta of xy, right? This is just the absolute value of xy, is delta of x times delta of y. And if x and y are non-zero, as they're supposed to be, then this is greater than or equal to delta of x, right? Delta of y is at least 1, because this has to be a non-negative integer. Right. So that implies that this delta satisfies the first part of the definition. Okay. Right. So this is for x and y not equal to 0. Okay. And then 2 is that we already have the division algorithm, right? So we just use the usual division algorithm. In the usual division algorithm, the remainder that we get is positive and less than the thing we're dividing by, right? So in absolute value, it's less. One thing maybe to emphasize at this point is that for a Euclidean domain, your quotient and remainder in that expression don't have to be unique. So it would be perfectly okay in the division algorithm here. So it would be perfectly fine to write, say, just thinking this example off the top of my head, to write 5 as, so say we're dividing 5 by 3, it would be perfectly fine to write 5 as 3 times 2. So this would be, so this is your A, this is your B, and this is your Q, and then your R be -1. Right? Perfectly fine expression for A in terms of B as far as the definition of a Euclidean domain goes, because the key thing is that the absolute value of -1 be less than the absolute value of 3. Okay, so we lose the uniqueness of the expression for A, but that's fine. We gain a little flexibility that way, so that's perfectly okay. Okay, the other example is when R is the ring of polynomials over a field, and delta of f of x is equal to the degree of f of x. Right. So this makes an integral domain, and see the first property, if we look at delta of f of x, g of x, right, that's the degree of the product, that's the sum of the degrees, so that's delta of f of x plus delta of g of x. Right? And this has to be at least 0, so this is bigger than or equal to the delta of f of x. Right? So delta of any f of x is less than or equal to delta of f of x times g of x, as required. And 2, again, we just have the usual division algorithm for polynomials. We explicitly constructed a division algorithm for polynomials that gives you a remainder that's either 0 or of degree less than the thing you're dividing by. And in that case, our division algorithm always produced a unique quotient and remainder. Okay. Now we'll see a new example of a Euclidean domain, and that's the ring of Gaussian integers. So let's look at the ring of Gaussian integers, and delta of x, if x is a Gaussian integer, will just be the norm of x squared. Or maybe I'll say r. Okay. And then write r is x plus I, y, right? X coordinate, y coordinate. And then this thing is just x squared plus y squared. Right, just to remind you, and right, so yeah, so two things. I already said previously that that delta, this delta of a product is the product of the deltas. Right, so this is delta of R, delta of S, and yeah, and if S is a Gaussian integer, right, you have the sum of squares of two integers, and if S is non-zero, those are they can't both be zero. So this is going to be at least 1. Okay, so this is bigger than or equal to delta of R. Right, so this is because this is using the fact that S is a Gaussian integer, so it's at least its x or y component has to be at least 1, so the norm squared of it is at least 1. Okay, so that's the first property of the Euclidean domain verified, and then we have to look at the second property. So if we're given A and B not equal to 0, what we want is to write A is equal to B times Q plus R. Right, so we have to figure out what's Q and what's R. Right, so what is this and what is this? We need some way of constructing them. I'm going to show you more or less explicitly how to figure out what those should be. So basically, we start with this equation, and so A is equal to BQ plus R. That's equivalent to A over B is equal to Q plus R over B. Right? And I want this to be a Gaussian integer. So I want that to be a Gaussian integer. And what else do I want? I want R to be small relative to B. Right? I want the norm square of R, the distance that R is from the origin, to be smaller than the distance squared that B is from the origin. So their quotient is the norm squared of that is going to have to be less than 1. So I want this to be small, right? So basically I want Q to be as close to A over B as I can get it, right? So this is some complex number, right? This is no longer a Gaussian integer. I'm dividing two Gaussian integers. Gaussian integers are not a field, so this is just going to be some complex number. But what I want to do is find something in the Gaussian integers, which is as close as I possibly can get it to A over B. So let me just draw you a little picture here to hopefully help you out. Get rid of all the chalk on this eraser. Okay. So let's say that A over B is equal to C plus DI. Okay. Now, how do we think about this? Well, the Gaussian integer, so here's the complex plane. Right, so this is the x-axis and the y-axis, and this is 1, this is I, right? Those are Gaussian integers, and every other integer thing. So I go an integer amount this way and an integer amount this way, right? This way and this way. So I just get this. I get this lattice. People often call it a lattice. Lattice points of the Gaussian integers. Right, so I get some picture like this. This is what the Gaussian integers look like in the complex numbers. And I have my A and my B in hand, and I look at A over B. Right, that's some complex number, C plus DI. In fact, it's C and D have to be rational. You can check, but that's not too important. You can just think about these are real numbers. This lands in the complex plane somewhere, and so let's just visualize. Let's say it lands here. Okay, so let's say this is C plus DI, right there. Well, let me blow this picture up a bit. So what I have these 4 Gaussian integers on the corner of this, right? So it's got to fall in one of these boxes here. So my C plus DI is here. C plus DI is right there. And what I want to do is I want to pick a Gaussian integer Q, which is as close as I can get it to this thing. So it looks like in this picture I should pick this one, right? So the separation between them should be as small as I can make it. And that's not necessarily a unique choice, right? For example, if this fell squarely in the middle of this box, then I could pick any of them and they would be equidistant. So it doesn't matter. We just want to pick one that's as close as possible. And the way we can do that is the following. So you can look at, so this C here, right? C falls in some interval of real numbers between two integers, right? So this C has to be between two integers, right? And also D, the amount it is up this way, has to also fall between two integers. And well, it's got to fall in that interval of between two integers, it's got to fall on one side or the other, or maybe directly in the middle. But in either case, no matter what we can do is we can find m and n in Z such that the distance between C and m is less than or equal to 1/2. Right? It's either, it's basically just the closest integer to C. There's got to be one at least no more than a distance of 1/2 away from it. And D minus n is less than or equal to 1/2 as well. Okay, so those are the integers that are close, maybe not unique, but integers that are closest to C and D. Okay, and then that's going to be our Q. Remember, that's what we were trying to do. We were trying to say what Q was. So Q is going to be this m plus n times I. Okay, so this is our definition. Right? We can compute A over B, find C and D, find the closest integers to it, and then define Q that way. Right? So that's how you define Q. And then just remember we had well, what we're trying to do is write A is BQ plus R, right? But we had A and B, we defined Q, so R, there's only one possible choice for it. So you define Q this way, and you then define R after the Q to be A minus BQ. Okay? And then I claim with this that the norm squared of R is less than the norm squared of B. And basically want to make use of this fact here. So what we can do is, right, so what I want to do is look at, remember again, this is A over B equals Q plus R over B, right? And so what we know is that, so what we want to do is check that R over B is small. And so what we're going to do is look at the norm of R over B squared, right? Because I want norm of R squared to be less than norm of B squared. So I'm going to check that this is norm squared is less than 1, and then that'll follow. So this is the norm of A over B minus Q squared, right? And A over B is C plus DI, and Q is M plus NI. So this is going to be C minus M plus D minus N times I, right? So that's what this complex number is going to be there. All right, so this is going to be C minus M squared plus D minus N squared. Because this complex number just has C minus M and D minus N as its components, right, as you can see explicitly. Okay, and C minus M, well, that's less than or equal to 1/2, so its square is less than or equal to 1/4. And the other one the same, right? So this is less than or so this is equal to 1/2 here. And 1/2 is strictly less than 1. Right? So the norm of this complex number squared is less than 1. So it immediately follows that the norm squared of R is less than the norm squared of B. And that exactly says that delta of R is less than delta of B as required. Okay, so that's how you do the division algorithm in the Gaussian integers. You just divide your Gaussian integers as complex numbers and then find the Gaussian integer, a Gaussian integer which is closest to that complex number, and then the difference is going to be, essentially the difference is going to be the remainder. So that's how you define Q, and then you define R so as to make this equation true. Okay. So that says that the Gaussian integers are an integral domain. And you'll see a couple other examples when you do the homework. Okay, so there's examples that are kind of similar to the Gaussian integers. Okay. And now we're going to look at just some consequences of the definition of a Euclidean domain, and then we'll be done. Okay, so just hopefully relatively short lecture for today. Make sure this is fully visible here. Okay, so let me just remind you the key properties. So Euclidean domain. Right, so the key things is that one, essentially, I like this formulation, that A divides C implies delta A is less than or equal to delta C, right? And two is the division algorithm. So A equals BQ plus R, and R equals 0, or delta of R is less than delta of B. Okay. So those are two things to keep in mind. And let me draw you a picture, because I think it's helpful to conceptualize this Euclidean domain. So here's my picture. So this is a real line, but I'm just going to draw the integer points on it. So here's 0. So 0, 1, 2, 3, 4, etc. And over here we have R minus the 0 ideal, right? And then we have this function delta, which is taking R minus the 0 ideal to Z. And what we can do is you can think about the level sets of this function with respect in R minus the 0 ideal. So in other words, think about all the stuff that goes to 0, all the stuff that goes to 1, to 2, etc. Right? So all the stuff that goes to 0, I mean, some of these may be empty, right? So nobody says that, so for example, the degree function on polynomials, right, there's constant polynomials of degree 0, so that's a value there. But on the integers, right, remember, integers minus 0, the absolute value only takes smallest value 1, right, so it starts at 1. So some of these level sets could be potentially empty. But the basic picture would be, so you have all the stuff that goes to 0. So this is, you might denote that delta inverse of 0, right? All the stuff that sort of pulls 0 back here, looking at all the stuff that goes into it. And you can also, right, and then you have delta inverse of 1. And so you basically, I think about this R as kind of like rungs of a ladder, or different levels, right? So this delta function splits up your ring minus the 0 ideal into different levels. This hierarchy, it creates this hierarchy in your ring. And so that's the way I like to think about it. Right, so all of this stuff here, that's all mapping to 2. This is all mapping to 1. This is all mapping to 0. This is all mapping to 3. That's all mapping to 4, etc. Okay, and yeah, so just what this first property here says is that if A divides C, right, so if I have A here and A divides C, well, it has to be that C is higher up on the ladder than A is, right? So knowing A divides C means C has to either be on the same level as A or somewhere higher, right? So so we could have C is equal to B times A there, or C is equal to B times A there, something like that. So you can try to visualize this in terms of this picture, if that's helpful. So hopefully that's enlightening to somebody. Okay, so that's the picture, and we're going to look at some properties. So one thing you can notice just from the first property and the fact that a unit divides everything in a ring is that the value of this delta on a unit has to be less than the value of delta on any other thing in the ring. Right? So if you take A to be a unit and C to be some arbitrary element in your ring, right, then this is true no matter what that unit and that element are. So this has to be true no matter what that unit and element are. So we can formalize that. So here's the theorem. and what we have is that, right, yeah, so in this context, right, so we have an integral domain, or we have a Euclidean domain. So in this context, so if U is a unit, so let me say it this way, delta of U is less than or equal to delta of R for all units U and R in R, right? And then in particular, delta of U is equal to delta of V for all units U and V. Right, so that's one thing, and we'll show that carefully. And another thing is that if you have two things that are associates, they have to be on the same level in this picture. They have to be on the same level of the hierarchy. So if R and S are associates, then delta of R equals delta of S. Okay. Okay, so as I said, well, so the proof of 1 is quite simple, and it's just the fact that U divides R. Right, so U divides R because U is a unit and units divide anything whatsoever. So that means that delta of U is less than or equal to delta of R. Right? So the value of delta on a unit has to be less than or equal to everything else in the ring. But then if we apply this, so what happens if we let R be equal to some other unit, V, right? Well, then so if V is another unit, right, then, well, U divides V, right, because V is, some random element of the ring, but also V divides U, because now V is also a unit, and we can use U as our R, right? So V is also a unit, then V divides U, right, and U divides V, right? So that implies that delta of V is less than or equal to delta of U, and also delta of U is less than or equal to delta of V. So those two values have to be the same. So that implies delta of U is equal to delta of V. Okay, so what that tells you is that the bottom rung of this ladder is the value of, so maybe it might not be 0. So let me delete this here. So yeah, so this doesn't have to be 0. So let me not put labels, and we'll just put random dots here. And let's say potentially, so 0 could be down here. Right? But if this is the lowest rung on our ladder, then all of the units are down here, right? Because their value is lower than everything else. Okay, so that fills out some of this. So, so a chunk of this here. And actually, we're going to see that it's all of it. So everything on this lowest rung is actually a unit. That's not entirely clear right now, but we do know that all of the units have to fall on that lowest rung of the ladder. Okay, so that's part 1. And also, among these units is the identity, by the way. Okay, so that's a special case there. So basically, another way you could say this is the minimum value of this function delta is the value of delta on 1. That's another thing you can say. So we still have to prove 2 here, but that's fairly simple because if R and S are associates, that means that R is equal to S times U, right, which says that S divides R. But also this equation here is equivalent to S is equal to R times U inverse, because U is a unit, right? Because R and S being associates, that means this U is a unit. So this says that R divides S. Right? So again, because S divides R, delta of S is less than or equal to delta of R. But if R divides S, that means delta of R is less than or equal to delta of S. So those two values are equal. So this implies that delta of S equals delta of R. Okay. So that says that all of the associates are on the same level in this picture. So I kind of like to picture this like this. So here's your lowest level here. So in the lowest level, you have the units, right? So these are all the units. And then maybe you have something else. We're going to see that you don't. But it could potentially, right at this point, be that there's something else here and the associates of all this things. So each of these little bars is representing the equivalence class of some element of your ring with respect to associate. So pick something in here, everything else here is the associate of that thing. And that's true of every level, right? So if I have something in this level, all of its associates are in the same level, right? So I can look at all of that thing's associates. And then I pick something else and look at all of its associates, and something else and look at all of its associates. Right? So you might, you kind of get a picture, roughly speaking, like this, that every level, whoops, I don't even have a level corresponding to that. That every, right, so this delta function breaks up your ring into this hierarchy, into these levels, and each level is broken into equivalence classes of associates so mutual associates. Okay, so that's the kind of picture we get from the definition and from that theorem. Okay, and so as I was saying, we know that all of the units are at the lowest rung of this ladder, but what we might wonder is whether there's anything else that's not a unit on the lowest rung of this ladder. And it turns out that there is nothing else, that actually everything at the bottom is all of the units, and that follows from the axiom. So far we haven't used the second axiom, so we need to use the second axiom to see that. So let's take a look at that. Okay. Oh, right, I should leave this up here. Okay, so let me state that theorem. So this theorem is going to be the last thing we look at for today. Okay. So here's the theorem. Okay, so so R is an Euclidean domain, and U is not equal to 0. Then the following are equivalent. Okay. One is that U is a unit. Okay, so we saw that if U is a unit, right, then U is on the bottom rung of that ladder, and 1 is down there as well. So that immediately implies 2, which is that the value of delta at U is equal to the value of delta at 1. Right, so we've already established that. Okay, and this is a particular case of the following statement. Delta, so the third thing that's equivalent to saying that U is a unit is saying that delta at some non-zero C has the same value as delta at U times C. Okay, for some, so I'll expand on this a bit. So for some C not equal to 0. Okay, and you can immediately see that 2 implies 3 because you can just take C equal to 1. Right, so this just says for some C. So if 2 is true, then just take C equal to 1, and we see that 3 is true. The interesting implication here, the thing we really have to prove, is that 3 implies 1. Okay, and what does 3 say? So 3 says basically you can think about it this way. So remember that our delta here, if A divides C, then delta of A is less than or equal to delta of C, right? And this third thing is basically characterizing the equality case. So what happens when A divides C and delta of A is equal to delta of C? Right? Then what this third thing is saying is that A and C, in this case, right, so when equality is achieved here, A and C actually have to be associates. They have to differ by a unit. right? So this number 3, this is saying delta of C is equal to delta of UC, right? And this U is just right now in 3 is just some random non-zero thing here, right? So basically what we have in 3 is that we have the value of delta at something in the ring and its value at a multiple of that thing, right? So here we have is C is dividing this thing here. And so we have C dividing something, right? So something dividing something, and the value of delta is equal there. And so what this third thing is saying is that if that happens, then that multiple there, that has to be a unit, okay? So that would mean, so if U is a unit, then C and UC are going to be associates. Right? So basically, this is characterizing the equality case of what happens. So what happens in the equality case of 1 there. Okay, so that's kind of the meaning of this proposition. So, right, so as I said, we just need to prove that 3 implies 1. Okay, so we need to prove, I'm very much out of room here, so let me see. So we need to prove, okay, so the proof, we just need that 3 implies 1. And so i.e. that if delta at some non-zero C is equal to delta at some multiple of C, right? Right, then that implies that U is equal to, U is a unit. Okay, so that's what we're trying to deduce here. Okay, right, so as I said, so as I said, so what we should be thinking about is that the main thing here is that this C divides this UC, right? And so it turns out it's really its equivalent. So saying U as a unit is really just saying that these two things are associates. C and UC are associates. So one thing about that is that if two things are associates, then they mutually divide each other, right? So So we see here C divides UC, but it's not obvious that UC divides C, right? Because we don't know that U is a unit yet. That's what we're trying to conclude. So what we're going to show, we'll show that UC divides C. Okay, so there's something else we can multiply UC by to get C. And then, so if we do that, if that holds, then what that means is that UC times some V is equal to C, right? And because we have an integral domain, no zero divisors, so we can cancel the C's, right? And that implies that UV equals 1, which implies that U is a unit. Okay, so what we've just shown is that if we can show that UC divides C, then we're done. It does follow that U is a unit. Okay, so how do we do that? So we want to show that UC divides C. Okay, and the way we do that is by using the division algorithm, right? So we want to see that UC divides C, so why don't we divide C by UC using the division algorithm and see what happens. Right? What we want is for R to be equal to 0. So let's suppose that R is not equal to 0. Suppose 0 is not equal to R. Right? Well, just rearranging this equation here, so the thing is we have C's in both places, so if we pull this over here, we get C times 1 minus UQ. Right? Then R is... so R is divided by C, right? So C is a divisor of R. So this implies that C divides R. And what we know about our function delta is that that immediately implies that delta of C is less than or equal to delta of R. Right? So that's something immediate. But Well, but there's something else we know about r, right? That we haven't really used the main thing, is that if r is not 0, then delta of r has to be less than the thing we were dividing by, which is UC in this case, right? So this is, excuse me, not equal, less than delta of UC. And, well, by hypothesis, right, delta of UC was equal to delta of C. Right, but now we're in the absurd position of delta of C being less than itself. Right? So that can't happen. So no matter what delta of C is. And so that means that R cannot be equal to 0. So this is a contradiction. And that establishes that R must be 0. In other words, UC divides C. And we saw that that implies that U is a unit. Okay, so that completes the proof of that proposition. All right, and right, so as I said, yeah, so that sort of completes that fills out more of the, fleshes out more of the picture associated with a Euclidean domain. So here, over here we have Z, we have R minus 0, and we have this function delta here. And we have these different levels. So let's say this is the minimum level here, then everything down here is a unit, as we just saw. Everything at the bottom level has to be a unit. So if delta of U, right, delta of a non-zero U equals 1, that was the second point of that theorem, that just going around following your equivalent, right? So it implies that U is a unit. So if you're at the same level as 1, right, so 1 is down here at the lowest level we know, so everything else down here has to be a unit. So this is all units down here. Right? And then at the other levels, you have, and all those units are associates of each other, right? So this is one big block of associates, which are units in this case. Right, and yeah, so then you have all the, various associates of other elements of your ring here. And what we found is that if right, so basically what we said is that if A divides C, right, and delta of A is equal to delta of C, right, so we know this implies less than or equal to, but if it's equal, right, so A divides C, that means that this C here is equal to A times B, right? But we just saw that that implies that B is a unit, so that means that that implies that A and C are associates. Right. So you can't have, right, so basically what this says is that let's start with A. So if I start with A here, the only way, and I multiply A by something, the only way I can remain at the same level is if that thing I multiplied by was a unit, right? And so that moves me around in the associates of A here. Right, so let's see. Yeah, so you have associates of A, those are multiples of A, and then let's see, so you have C could be up here that's a divisor, or that's something divisible by A. So you can either have up here or on the same level or a unit. So if you're looking at if you start with A and you look at, start with C and look at the things that divide it. If it's on the same level, that has to be an associate of C. If it's on the lower level, it's either a unit, it's either all the way down here, or it's a non-associate of C. All right. Anyway, I hope that makes some sense here. Okay, so I think that's going to conclude the lecture here. That's as far as I got when I was doing the live stream. So, and we're at 1 hour and 10 minutes. So that's going to do it.